This sample problem deals with friction and removing kinetic energy from a moving car. The force of friction will deal with the braking system in a standard automobile that has a brake pad that presses into a rotor. So we have Aaron, 60 kilograms, driving a car that has a mass of 1,200 kilograms, and the car is coasting on level ground at 15 meters per second, so we're not speeding up, we're not slowing down. The motor is not engaged with the car, it's coasting. First, we'll do a simple calculation of the kinetic energy of the car, and then separately, kinetic energy for Aaron. Then we want to calculate the force of friction for the brakes needed to stop the car in a distance of 25 meters after the brakes are applied. The brake pad is applied on the rotor at a distance of 9 inches from the axle. And effectively, it's spread out, of course, a little bit more than 9, a little less than 9, but we're going to call it the force is being applied at 9 inches from the axle. And the overall diameter of the rubber tire of the car is 30 inches. Then we're going to assume the same force of friction for the brakes and calculate the distance required to stop the car if we up the speed to 30 meters per second, if we double the speed from what we have in Part B. So let's see how the calculations proceed. You should read the problem a couple times. After you read the problem, then make a sketch with some of the important information. Simple sketch is fine, doesn't have to be artistic. But simple calculation to start with, kinetic energy is 1/2 mv squared. So 1/2, 1,200 kilograms for the mass of the car, 15 meters per second that's squared, and 1.35 times 10 to the 5th joules. For the person, the mass is different, 60 kilograms. The speed is the same. They're a person traveling in the car and the person have the same speed. But we have less mass, so the kinetic energy is smaller, 6.75 times 10 to the 3rd joules. How could we check to see if these two numbers are reasonable? Well, 1/2 mv squared, if v is a constant in the two calculations, then kinetic energy is proportional to mass. Well, the car's mass is 20 times the mass of Aaron, so the kinetic energy should be 20 times, and if you take these two numbers and divide them, you'll come up with 20, so that seems reasonable. What is the force of friction if we're going to stop the car in 25 meters? Well, to stop the car, it means we need to bring the kinetic energy down to 0. So we have the two kinetic energies calculated. We'll add those together to get the total kinetic energy of the system. And the brakes are going to do work on the system and remove kinetic energy. The work done is force times displacement. Here we need to consider that the force of friction and the motion of the rotor past the brake pad, these are in opposite directions. Friction always works opposite to the direction of motion or the tendency to move in the case of static friction. So that theta is going to be 180 degrees, and we're going to have a negative number for the work. And that's reasonable because we want to reduce the kinetic energy. So the work number should be a negative. So the change in kinetic energy, kinetic energy final minus kinetic energy initial, is the work. So let's proceed here. We're going to need to talk a little bit about the details of the brake system. This is not for an electric vehicle that uses electromagnetic interactions and recharges the battery. This is a simple car that has a brake pad, the simple drawing here in blue, the brake pad, that rubs on a rotor. This gray symbol here, gray circle, I've taken to be the rotor of the wheel. And the force of friction is, I'll take here right at this drawing to be off to the left. The rotor is going to be moving to the right past the brake pad. So when you put your foot on the brake pedal, there's a hydraulic system that engages and presses this brake pad into the rotor, presses it into the rotor. and that creates a frictional force. There's going to be a normal force, a contact force, between the rotor and the brake pad, and that's going to lead to a force of friction. We do have four wheels in the car that I'm modeling here, and we're going to assume we've got the same interaction on each of the four wheels. So each wheel, each brake system, is going to remove 1/4 of the kinetic energy. We'll get to that in a minute. So let's suppose that we have this 9-inch distance from the axle to where our force is, where the rotor is, and we want to think about, as this wheel is turning, it's turning this way, what distance does the rotor slide past the brake pad? Well, we're on a circle here with a radius of 9 inches. We're going to need circumference, so let's change our inches into centimeters, and then we'll change it to meters. But 2.5 centimeters is 1 inch, so our brake pad is sitting here effectively 22.86 centimeters from the axle. When the wheel rotates one time, the wheel rotor is moving past the brake pad for a distance of 2 pi r, one circumference, 2 pi times 0.2286 meters. So that's 1.436 meters. We'll need this number later. 1.436 meters of displacement past the point of friction for one rotation of the wheel. What about the car itself? For one rotation of the wheel, the car is going to move the circumference of the wheel. So 2 pi and 30 inches for diameter for the wheel, 15 inches for the radius. Again, converting into meters with 0.0254 meters is 1 inch. And the car is going to move 2.394 meters down the road. So perhaps pause and think about this again, but 2 pi r gives a circumference. Imagine a piece of string wrapped around the wheel, and we tape it down to the roadway and let the car roll forward. That string is going to unwind 2.394 meters for one rotation of the wheel. So I'm copying those numbers, nothing new here. Copying those numbers so we can take some advantage of make it a conversion factor. How many rotations of the rubber tire will occur when the car goes 25 meters down the road? Well, one rotation moves the car 2.394 meters. So I use this conversion factor to cancel off meters and get to rotations. The tire has moved 10.44 rotations. As the car goes down the road, the wheel has rotated 10.44 times. How far has the brake pad moved past the rotor? Why we're doing this is because work is force times displacement. We want to know the displacement, the distance that the rotor has moved past the brake pad. So 10.44 rotations, we get 1.436 meters for one rotation. We get 15 meters of motion of the rotor past the brake pad. Now, what about the force of friction? Well, again, the change in kinetic energy is equal to the work done by friction. The final kinetic energy is 0. We want to come to rest. Our initial kinetic energy is the kinetic energy of the car plus the kinetic energy of the person in the car. We calculated those earlier. So we sum those together. This is the total kinetic energy of the system. The displacement of the rotor is 15 meters, so I've got a number to put in here. I've got a number for the kinetic energy initial. And cosine of theta, we're going to get a -1 for that, so the minus signs will agree. And again, reminder here, we've got four wheels where these brakes are being active. So each brake, each wheel, is going to remove 1/4 of the kinetic energy. So I take the total kinetic energy initial and divide by 4. This is going to give us the work done by one brake system. That's the force of friction multiplied by the displacement of the rotor sliding past the brake pad. So you ought to pause this, pull out your calculator, and check your calculations that perhaps hopefully agree with mine. I came up with a frictional force, 2.362 times 10 to the third newtons. I keep an extra digit in my intermediate calculations. In fact, I don't round off what my calculator shows if it's an intermediate calculation. But we were asked to find the force of friction. Now I'm going to round to 3 significant figures. That's typical for homework problems, especially if I assign them. 2.36 times 10 to the third newtons. That's our frictional force. This is occurring at one wheel. Okay, let's say we have the same force of friction. Our hydraulic system is working the same, but now the speed of the car has doubled. We're to 30 meters per second. We want to stop the same car that's moving at 30 meters per second. How much distance should we allow? Well, the kinetic energy now is different. We're up to 30 meters per second instead of 15. So 5.67 times 10 to the fifth joules. And this 1260, that's the mass of the car plus mass of Aaron. So 1/4 again of that kinetic energy for each wheel, each brake system on each wheel. So taking this total kinetic energy divided by 4, we use the same force of friction. Now I'm keeping this extra digit in that intermediate result I had earlier, so I get a little bit more accurate number for x for the displacement. So again, pause the video and pull out your calculator. I came up with 60 meters of motion across the brake pad. I wonder if that's reasonable. Is that reasonable? Let's think about this a little bit. The 60 meters is one rotation divided by 1.436 meters of displacement at the brake pad. So we've occurred 41.78 rotations now for this case. And then we have a number of meters for one rotation. So we've moved 100 meters to stop the car. It took 100 meters. If you recall, previously for the 15 meters per second, that took 25 meters to stop. Is it reasonable that the stopping distance has gone up by a factor of 4? Well, yes, because work is force times distance for the case of this brake system. And we have 4 times more work that's required. There's 4 times more kinetic energy. So now the stopping distance needs to be 4 times greater, so 100 meters. So be careful when you're driving. If your speed is doubled, your stopping distance does not double. Your stopping distance goes up by a factor of 4. So obey the speed limits, look ahead for traffic, and so forth. If you want to see some more of descriptions of my YouTube videos, go to my simple website, gpclements.com. I've created an annotated listing of all my YouTube videos, physics and astronomy and some other miscellaneous topics. This annotated list tells you the title of the video, how many minutes the video takes, a description of the video, and perhaps most importantly, there's a direct link to the YouTube video. You don't have to search on YouTube. gpclements.com has all the content organized by topic. After you find the one you want, you click on the link and you're at YouTube listening. All this content's free. You're not allowed to resell it, but you're allowed to use it without any registration being required. I don't pull up your name or email address, anything. And my website does not put cookies on your computer. So keep working physics problems. Ask your instructor when you have a question.